So the first new feature is that we have introduced 5 new section types in AxisVM X6, and all of these cross sections are thin-walled parametric cross sections. The first one is the SFB section, which is an I section having a strengthening plate at the bottom flange. It is available both for welded and rolled type of I sections, and the width and the thickness of the strengthening plate can be controlled using the parameters. The second one is the IFB shape. It's very similar to the SFB, but in this case, the lower flange of the I section is cut off. Next, we have the HSQ section, which is a closed section having an overhanging lower flange. This type of course, it is only available for welded type of sections. And we have the asymmetric pair for the HSQ, which has similar parameters, but the lower flange position can be controlled through a dedicated parameter. And lastly, the fifth section is the crossed I shape or Maltese cross section, where the I sections can be either welded or rolled, and the section itself has to be symmetric. Moving on to the eccentric beam functions. Now we have the option to define beams and ribs eccentrically to their logical axis, and this is available for line elements. The first type of eccentricity which is being showed currently is the uniform offset. In this case, the eccentricities are constant along the member and can be set by radio buttons representing selected points of the cross sections, or we can choose to manually give eccentricity values measured from the logical axis of the cross sections. So local X and local Y and local Z values can be defined for eccentricity. The next option is to set the eccentricity automatically by aligning to an eccentricity group. In this case, the E, Y, and EZ eccentricities of the element smallest in the respective direction will be set to 0, while other elements will shift so that their selected point on the bounding rectangle remains. This is suitable, for example, defining tapered members like on the example. And lastly, or not lastly, but the next option is when we align a member to another member, which is a common case when, for example, a beam sits on top of another one. And in this case,
we have to select the members which we want to make eccentric, and then select the reference members on which the eccentric members will sit on. The eccentricity will be set based on the height of the reference members, both on start and end points. In this first example, we have a tapered frame where we will use the uniform offset function. We will use it to set the top flanges of the members for the eccentricity reference, and by this we are able to align the outer flanges of the beams and columns properly.
Next, we have a multi-story building where we have ribs connected to the domains. And these ribs are defined between the columns. Each rib have tapered start and end sections. And using a simple click on the rib eccentricities, we are able to set the upper plane of the ribs to align with the upper plane of the domains. Eccentricities are adaptive in a form that if there are changes in the connected members' cross-sectional or positional properties, it will be adopted by the positioned eccentricities also. So for example, here we are changing the cross sections of different members, and as you can see, the eccentricities changes properly and updated properly. Beside members, loads can also be set to eccentric positions, both for point loads and line loads as well. The eccentricity options are available from the load definition dialog, and if it is enabled, we can choose from cross-sectional points such as upper flange on the right, left side, and as you can see on each dedicated point of the cross sections. And we can also use custom values for the eccentricities with the radio check button. And as you can see, the bending moment component is automatically calculated, and this bending will be placed on the model alongside with this eccentric point load. And this will, of course, result in a rotation of the cross section, as you can see. In this case, we will have a torsion as well. So using these eccentric beam and load functions, we can model and design our structure more precisely, more realistic, and the effect of these eccentricities are taken into account during the calculation. The next new function is the Winkler-Pasternak support, which is a new type of support available both for line and surface supports. So with this, the underlying soil behavior and therefore the displacements of the structure can be modeled more precisely.
Winkler-Pasternak support can be defined from the support dialog as well, using the dedicated radio button. And the difference between the Winkler and the Winkler-Pasternak support is that the Winkler-Pasternak support elements represent a Winkler-type elastic foundation against rotation and displacements in local X and Y directions, but against local Z displacement, a Pasternak layer is introduced above the Winkler foundation layer, and this layer has a constant shear stiffness.
On the example model, we have a moving point load defined on the beams, and to be able to see the difference between the two support types, the modulus of elasticity is set to 0 for the beam material. Yeah, these are the point loads moving on top of the beams, and these are the displacement results for both support types. As you can see, the upper one is the original Winkler type, the lower is the Winkler-Pasternak, and the displacements are more even, and in case of the Winkler type, displacements are locally present. The next example is very similar for the beam type. This is using a surface domain. And again, we have to set the shear stiffness for the Pasternak layer. And after running the linear analysis, we will see that displacements in the Winkler-Pasternak supports are much more even than in case of the simple Winkler type. Okay. So the next function is the custom rules for load combination generation. And to introduce this new feature, we will use this model as an example, which is a multi-story building. And using this feature, the user can have more control over the critical combination generation process. And the model has quite a few load groups. Live loads are defined for each stories. Two of the top stories can either have a function as office or as residential floors. There are wind loads generated, defined for 4 different directions. And there we have a snow load group as well. If we would leave the critical combination generation for the program, we would end up probably several, maybe thousands of load combinations, which is often not ideal. Takes a lot of calculating power from the machine, and it would be also not be able to handle the 2 top stories where the function can either be office or residential area. So we have introduced a new function to create custom rules to generate load combinations by exclusivity or linkage between different load groups, and it is available through the table browser. By default, as you can see, all the load groups are listed and has an active label, which means that each will be included in the combination generation process. These are actually drop-down menus and can be modified so certain load groups will be excluded from the combination generation. On the first example, 2 rule is created, which states that the second and the third floor office function cannot be combined with the residential function of the same floor, and meteorological loads are also excluded. On the next example, we can put load groups to simultaneity groups. So the load groups of the same simultaneity group will always act together. In this example, snow load is acting together with one of the wind loads. On the next example, we can also use the same method to put load groups to a leading group, which will act together. In this case, the second and third story load groups forms one leading group, while having the simultaneity groups as well. And if we have more than one load group in a leading or simultaneity group, we will have the option to create another leading or simultaneity group, like in this example, putting the first floor and the lounge load group in leading group 2. So in this way, we have a control over the load combination generation. And let's assume that we have covered all the necessary type of load combination we want to generate for our structure. In this case, on this particular model, using the custom rules, we have 978 load combinations generated, which is quite a lot. But if we would leave everything as default, so every load groups would have the active label, as you can see here. All load groups are set to active. In this case, the load combination generation will produce more than 100,000 combinations. So definitely the custom rules can help to lower this amount. Next, we will take a look on the improvements of the result visualization front. First one is that the results are now displayed on the, or can be displayed on the rendered model. If a result component is displayed with the solid model display mode, result will color the render model, where elements will be displayed with their actual physical dimensions. So these are the displacements, but it is available for each result component. So internal forces, as well as stresses, surface internal forces, etc. And of course, rendered view works for domains, but it works for steel members as well. So for example, we can visualize the changes in the axial stresses of a beam pretty nicely. So these are the minimum and these are the maximum values of the normal stress. And if we choose the min-max value, we can see that how the normal stress changes along the member. So as you can see, the top middle sections, top flanges are compressed, while the lower flanges at the middle are tensioned. There are some minor improvements on the color legend palette settings as well, where we have a new button to automatically separate positive and negative values for a selected result type. And staying with the normal stresses, compressed and tension parts of the beam separates quite visually. This can also be used, for example, about any other result component, but in this case, normal forces displayed, which can be useful for trusses, for example, to separate compressed and tensioned members, but it can be handy when displaying reinforcement differences. The next example is a small improvement for the color legend. We can use custom values for the minimum and maximum values of the legend and set that the results above and below these values will be hatched and displayed transparently. As you can see, this is the min-max values of the normal stresses, and above and below a certain value, results are hatched and visualized transparently. Next one is a new option when searching for minimum and maximum values. So now you can keep the selection by ticking the checkbox on the search window, and by that, when the program finds the result, the member which have the minimum or maximum values of the searched result, the element will stay selected. So in that way, you can easily find the members, which can be helpful in a bigger model. Of course, this is a quite simple example. Next one is the semi-autocritical combination generation. So when scrolling through different analysis results for critical combinations, each result component will be displayed according to their respective corresponding combination formula. For the first example, but if we leave the critical combination formula on auto, that will mean that the maximum envelopes for normal forces, as you can see here, so these are the minimum values for normal forces, will come from ULS type of combination, while if we're choosing a displacement result component, they will come from SLS characteristic formula, as you can see. If we set the critical combination formula to custom, that will mean that each result formula will be listed in the drop-down menu, and there we can individually check the results for each combination formula. These were pre-existing in previous versions, so X5. So now quasi-permanent were selected and quasi-permanent results were showed. But now we have a semi-automatic formula, and this means that AxisVM uses ULS or SLS combination according to the type of calculation, but the formula for creating SLS combinations can be chosen. So for example, if we check the normal forces, you will see that they are coming from ULSV formula, while checking the displacements, we have previously selected on the dialog the SLS frequent option, and this is what is used for the calculation of the displacements. Next, we have tracking results for calculated reinforcements. Basically, after the definition of the reinforcement parameters, the program will automatically calculate the crack width for the required reinforcements.
The crack width calculated for required reinforcement can be considered only as an approximate value, because the final actual reinforcement will be different from the required reinforcement.
So until AxisVM X5, crack width were only calculated if we have actual reinforcement defined on the domains, and from now we will have the option to estimate the cracking width based on the calculated reinforcement values. The calculated crack width for calculated reinforcements are highlighted with an asterisk on the upper index. We also have some improvements in the table browser for reinforcements. So now we have a table for specific amount of reinforcements, which can be checked for load cases, combinations, envelopes, critical combinations as well. So in this table sums up the areas, volumes, masses of reinforcements for each domains, which can be useful for example, pre-calculations. It is important to note that this is only the calculated reinforcements, and the table does not cover reinforcements from detailing rules, anchoring lengths, and etc. So it should be handled respectively. Next one is the RC2 module, where we have calculation report for concrete columns. So far, this was not available in X5. So yeah, actually starting with a smaller improvement that currently, similarly to the main user interface, predefined window layouts can be used also in the reinforced concrete design interface. So you can choose what layout you want to use. You can divide further each window. And if you click on the design calculation button, you will see that detailed calculations will be available. And of course, this can be exported, included in the documentations, just like any other detailed calculation view. Another small improvement, that column internal forces can be pasted into the check table, and they can be saved, or they are saved automatically after the module is closed and reopened as well, and represented on the normal force and bending diagrams. Next one is the shear check for concrete walls. Concrete walls are represented as virtual strips in the program. So selecting one wall, and we will use the first story to design. And shear utilization cannot be summed up by the utilization coming from the normal force and bending interaction, so it has to be requested separately on the parameters dialog after opening the wall reinforcement check dialog. And in addition to the shear check of the cross section, the check of sliding shear can also be selected and performed. Parameters are the roughness of the interfaces, and they can be set. The walls are only verified against shear forces parallel to the wall, and in the result window, basically you see a side view of the wall and its reinforcements, the design shear force and the shear resistance with the blue line. And in the case of sliding shear, which is enabled in this case, and it is the middle diagram, the design shear force at the bottom of the wall and the sliding shear resistance with the blue line. So far in AxisVM X5, we only had the option to define trapezoidal steel decks, but we were not able to calculate reinforcements for them, which we have now in AxisVM X6. And to present this function, we will use this steel hole, which has two podiums on its two sides. And the domain of this podium is defined as a trapezoidal steel deck sitting on top of supporting beams. The domain dialog for the steel decks is slightly extended compared to the X5 version. It contains two new parameters which represents the shear connection between the steel plate and the concrete. Eta represents the shear connection and expresses the proportion of the full compression resistance of the upper concrete layer transferred to the trapezoidal sheet. And if it is equals to 1, it represents a full shear connection. If it is lower than 1, the bending resistance of the slab will be lower, of course. Moving on to the reinforced concrete design and opening the parameters dialog for the trapezoidal steel decks, we see that the dialog is slightly different than for traditional domains. Namely, for the directions of the rebars can be set instead of X and Y directions, they has to be parallel or perpendicular to the. We can set if we want to use a single layer, so one layer reinforcement can be given in the lower concrete plate, and bottom reinforcements cannot be defined. If trapezoidal steel plate used only as a formwork checkbox is checked, the software takes into account only the upper concrete plate in the equations, and it will neglect the ribs and the trapezoidal sheet. So in this case, reinforcement parameters and concrete covers can be defined regarding in X and Y reinforcement directions. We will consider the trapezoidal steel plate in the first example. In case of composite slabs with trapezoidal sheeting, limiting crack width cannot be given on cracking panel, and as we will see, cracking is only calculated to the top part and not to the bottom. We will also have a warning message, which will notice that the trapezoidal plate is not verified against in construction stages, and also weight of the wet concrete is not taken into account as a load. So these are only warning messages for the designing engineer to keep in mind. So after we click OK, we will receive the reinforcement values for our steel deck, for our trapezoidal steel deck. And as you can see, this is the longitudinal top values, x directional top values, and because we have taken into consideration the steel deck for the lower reinforcement, the longitudinal bottom, so the y directional bottom reinforcement is not existent in this model because all of the forces is handled by the steel deck itself. And these are the x-directional bottom reinforcements. So for the other podium, we will use the same settings, but we will choose the option to not consider the trapezoidal plate in the calculation. And after clicking the OK button, we have the same warning message, and you will see that choosing the y-directional bottom reinforcement, now we have reinforcement needed for this bottom direction. Just quickly defining some reinforcements for the trapezoidal steel deck to see how the crack widths are represented. As I have mentioned before, in case of trapezoidal steel decks, we will only have the top side cracks calculated and not the bottom.